afternoon, and good evening, everyone. You're welcome to Next Gen. And today we are going to be talking about chemical engineering, the processes that produce everyday stuff. So we are really excited to have you here.
Good afternoon.
Good afternoon. Lovely to see you here today. It's a pleasure to have you here. I'll just like us, before we start, if you could just type into the chat where you have joined us from. We'll be glad to know. Yeah, good. Well done. So I'll just start by introducing myself and then AFB to you. My name is Dr. Urena Vivian Adegbotolu, and I'm the AFB Next Gen Coordinator. AFB UK is an organization that started in 2007, and we have here in Scotland, our leader is, and chairperson is Dr. Ollie Folayon, who you have the pleasure of seeing today. He's the one going to be giving the presentation today. And our chair as well, our co-founder as well, is Dr. Nike Folayon. AFB actually is a non-profit organization which also started here in Scotland in 2011. Now, AFB UK has four main branches or streams. And the first is what we are partaking in just now, and it's called Next Gen. Next Gen is a stream of AFB that focuses on young people and focuses on increasing their participation in STEM. And we do this by organizing school outreaches and online outreaches like the one you're having here. And our desire is to just increase the number of STEM professionals that we have in the future, increase the number of engineers, scientists, technologists, and mathematicians, economists, and so on and so forth. So the second stream we have in AFB is the transition stream. The transition is specifically for students, and what transition does is to prepare young people in university for the big world in terms of career development and employability. So in transition, they get to learn all about what they need to do in order to excel when they get their big jobs. And thirdly, we have another stream of AFB called Real Projects. Real Projects is a stream of AFB that is actually involved in teaching young people in university, that's students, as well as professionals, different subject matters that have to do with life projects going on in industry and showing them the pathways towards getting good solutions. And that way, young people are prepared for these questions when they arise in interviews as well as in their workplaces. And the fourth stream of AFB is the leadership stream. The leadership stream basically is for the professionals who are working and who are employed or who have their businesses. What the leadership stream does is that it prepares them to excel in their businesses and at their workplaces by helping them develop leadership skills, such as negotiation skills, organizational skills, and different skills that are required in the workplace. So today I want you to sit back and enjoy this presentation we have today from Dr. Ollie Folayon. Dr. Ollie Folayon is a chartered chemical engineer, and he working basically in the energy industry, and he's also a chairperson. He's actually an award-winning person. Dr. Ollie graduated with a BEng in chemical process engineering with fuel technology from the University of Sheffield in 1999. He earned a doctorate in fuels and combustion from the University of Leeds in the year 2002. He has authored 5 international publications in the field of combustion and engineering. To date, Dr. Ollie has worked on major CapEx front-end engineering, design, detailed design, and commissioning projects. In the year 2018, Dr. Ollie Folayan was accepted into the fellowship of the Institute of Chemical Engineers. Dr. Ollie has championed successful outreach programs such as Making Engineering Hot school campaigns in England, the Next Gen campaigns in Scotland, Transition and Real projects. He has co-authored 2 publications on the influence of role models in the transition from academic study to the workplace, and on the sustainability of the engineering profession in the UK. In addition, Dr. Ollie has also been involved with a number of successful community initiatives through organizations such as Shell and the Royal Academy of Engineering. Dr. Ollie has chaired a number of AFB UK annual seminars featuring key industry leaders and politicians, and is a regular speaker at events on varied engineering topics. Dr. Ollie is a member of the All Energy Diversity and Inclusion Task Group, set up in 2019 by the Oil and Gas UK. Dr. Ollie is an avid sports fan, and his interests include singing, mentoring, and reading. I want to especially welcome Dr. Ollie now to take the podium and give us his presentation. Dr. Ollie, you're welcome.
Yeah, thank you, Rena, for that introduction. I feel like an important person, but based on your introduction. But yeah, let me. What I'll do is I'll just very quickly share my screen and make sure I share the right one this time, because the last time I shared the wrong screen. So bear with me just a second while I do that. All right, hello everybody. I will just like to ask, how many of you have ever heard of the term chemical engineering? Who's heard of the term chemical engineering before? I have. I think I'm gonna have to do this a different way. Right, so when I was 9 years old, I read a book about a guy who was like an evil genius. He was able to use solar energy to do some really powerful stuff. And I remember reading the book, and I was driving, my dad was in the car and he was driving us somewhere. And I remember asking him, how many chemicals do chemical engineers make? And he just said to me, well, they make all of them. They make all chemicals. And I thought, right, that's it. I'm going to be a chemical engineer. I've been a chemical engineer now for almost 20 years. It's a very interesting, varied career, but it's one that people don't often know what a chemical engineer does. So what I'm going to do today is we're going to start with a poll. The question I'm going to ask you is this. We're going to ask you a question about chemical engineering. So I'll let Rena put the poll up. And you can tell us what you think a chemical engineer is. So let's start from that.
The question was, a chemical engineer is, The first option, 5% chose the first option, which is a chemist who likes engineers. The second option, 20% chose that, which is an engineer who likes chemists. The third option, 15% chose that, which is a wannabe mechanical engineer. And the last option, 80% of people chose that, which is a designer of process plants. So Ollie.
So 80% got the answer right. So we've started this off very, very well. So basically, some chemical engineers I know don't like chemists, so it's definitely not that answer. And some chemists I know don't like chemical engineers either, because so definitely the last answer is the right one. Chemical engineers design things. And so what I'm going to do today is I'm going to talk you through what a chemical engineer does. I'm going to then try and describe for you some of the processes that we work in. And I'll also give you a bit of history of how chemical engineering came to be as a field. And then we'll point you to a few examples of actual chemical engineers and who are doing other things other than engineering. Is that good? I'm going to wait for you to give me a quick answer and then I'll move on.
Yeah.
Yeah? Excellent, excellent. So I'm going to start by playing a very short video.
Yes.
About chemical engineering. So just a second.
I've chosen sunflowers to represent the connection to the business that we're in. So Syngenta makes crop protection products and sells seeds for agriculture around the world. And sunflowers are an important product. They're used for food, and their seeds and their oil is used in the food industry and for lots of other uses.
So this is my helmet. The reason I brought it along is because as a process engineer working on a production facility, I'd be lost without it. I need it if I'm going out into the units, which is a thing I love doing. I get the most learning when I go out into the fields because I can speak to the guys with 30 years worth of experience and really learn from them.
So here I have a prop with me, which for me epitomizes what chemical engineering is about. It's about fueling the world's needs, but it's also about innovation and technology. Here I have the greatest breakthrough for many years in terms of lubricants technology. There is nothing, I think, more exciting than being part of a team and being part of an organization that creates such a breakthrough. Chemical engineering is at the core of this project.
I've got here a jar of cocoa beans. Without cocoa beans, there wouldn't be Cadbury and there wouldn't be Mondelez. We start off with raw cocoa beans, which is extracted from cocoa pods. We then go on to make several chocolate products, such as whole nut, fruity nut, Cadbury. I love the idea of being able to walk into a shop and see products that I helped make on the shelves. And I love even more seeing people pick up those products and put it in their baskets.
One of the units I run is a furnace, and it actually uses hydrogen as a fuel source. So hydrogen burns with an invisible flame, which means that if there's a problem with one of the burners, you can't tell by looking at it. If you throw bicarbonate of soda into the air registers, you can see the orange flames track up the furnace. And as well as being really pretty, it's actually very practical, because it means that we can see if there's any problems with the burners or there's any flames that have gone astray. So the furnace flames are around about 10 to 15 metres high, and the furnace that they're in has 108 burners, so there's plenty of places to throw the bicarbonate of soda into.
So I've got a piece of sandstone here. It's called a core. It comes from about a mile under the Earth's surface, and this is the typical sort of rock that the oil and gas industries are involved in, also the water industries. Out of this rock obviously comes a lot of the feedstock. Many of the peat, light, power, transportation products arise within this rock. In today's world, we're also looking at injecting carbon dioxide into rocks like this.
So the prop I've brought today is a jigsaw. It's actually a Mensa jigsaw. I think it represents chemical engineering because Eng is all about problem solving. Every single day, every hour of the day, you will face a problem, and it's all about how you tackle it. And in general, it is about piecing the small bits of information together, whether it be pressures and temperatures or information from different people involved in the project, to get the overall picture and to find that solution.
Excellent, excellent. Did you enjoy that?
Yeah.
Fantastic, fantastic. So if I was to ask you, based on what you just heard, if you could put in the chat some of the things that you believe chemical engineers do, based on what you just saw, can you tell me some of the activities that chemical engineers do? So I'll just wait for a minute and let you put that in the chat. Make chocolate. I like that one. They make products. Excellent. Any more? Solve problems. That's the most important one. Dig up rocks and make beauty products. Fantastic. So based on that, I'm going to show you a number of companies that do a number of engineering activities. And what I'd like you to do is tell me which one of those companies engineers work in. So I will just share that with you just a second. Right. So my question to you is this: which one of these companies do not use chemical engineers based on what you just heard?
Intel.
Interesting, interesting. Who else thinks that Intel is the only one, or is the one that doesn't employ chemical engineers?
Question. I think L'Oreal.
Oh, okay. You think L'Oreal doesn't? Okay. That's all very, very, very interesting. And what I'm going to do is I'm going to show you as we go through this presentation what companies out of these actually employ chemical engineers. Chemical engineers, so I'll just tell you a little bit about myself. So when I was 9, I think I mentioned before, I read a book about an evil guy who was going to use solar energy and chemicals to make a lot of, basically to take over the world. And I remember being very fascinated by that. And I remember asking my dad about it. And what he said to me is that chemical engineers make all chemicals. So I thought, right, I'm going to be a chemical engineer. So I was just about this age in the picture on the left when I decided. And I've worked since then on many plants and on many projects. The one on the right, it was in 2006. I was working on a project in a place called Glen Mavis in Scotland. And what we were doing was starting up a huge plant. And I'll tell you a little bit more about that. So chemical engineers use principles of chemistry, physics, and mathematics, and economics to efficiently produce, design, transport, and transform energy and materials. Basically, our main goal as chemical engineers is to be able to take raw materials, and that can be anything, and to be able to convert it to things that people can use, and to be able to do that in the most economic, the cheapest way, and the most environmentally friendly way. So another name for us is process engineers. Chemical engineers are typically called process engineers. Now, the next question I'm going to find out from you is, what is a process? If I was to ask you what a process is, how would you define it? Just one suggestion.
I would say process is like it starts from one point and gets to another in different stages.
That is fantastic. That's a really good definition. Actually, one that really helps. So how many people here, as you can see, I've got a really, I've got a really nice breakfast here in front of me. How many of you have ever fried an egg?
Me.
Really? Wow. I'm impressed. So you what else have you cooked?
Scrambled eggs, noodles.
Oh, really? Oh, fantastic. So question is,
scrambled eggs.
yeah. So what's the first thing you do when you want to fry an egg?
You crack open the egg.
Oh, but where do you put the egg when you crack it open?
Put in the
You
pan.
get a bowl.
Yeah.
Oh,
Yeah.
sorry.
Okay. Okay. So what do you fry an egg in?
A frying pan.
A frying pan. That is perfect. So the first thing you do is you get the right pan, and then what do you put in the pan?
Oil.
Egg.
You just put the egg. Oh,
No,
oil.
you put the oil. Nothing.
Oil.
You put the oil. Fantastic. So that could be butter or it could be oil. What else? What do you do next?
You put the egg in.
Oh, don't you have to do something else to the pot first?
Turn the gas on.
Yeah, that's right. Turn the heat on. Fantastic. So you turn it up. Do you whack it up to the top? Do you whack up the heat to make it really hot, or do you make it just moderate?
Low heat.
Yeah, low heat. Nothing. You wait until the oil's a bit is hot so you can cook it.
That's fantastic. You are good cooks. I'm going to have you on MasterChef next time. So next thing you do, as you guys have said, you crack the egg into the pan, and then maybe you might want to put some seasoning or something on it so that it tastes nice. Now, this process that we've just been through, or these steps that we've just been through, is what is called a process. A process is a series of steps taking you, as somebody said earlier, from getting the raw material. In this case, you got your egg, you had your oil, you had all of those things, and what you wanted to do was convert it into something that you can eat and enjoy. And so what you did was you went through all of these steps, and that step is referred to as a process. So this is the time for our next poll. And our next poll is, I'll just wait for Mo or someone to give us our next poll. So the next poll is frying an egg. We'd like to know, is that a physical change? Okay, so we'll let you give us the answers now.
So the question was, frying an egg, is it a physical process? Is a physical process true or false? We had 35 people say it's true, and we had 65% say it's false. 67% now.
So give me the percentages again.
33% for true, and 67% for false.
Fantastic. Yeah. So you've given us the right answer. So most of you got the answer correct. The process of frying an egg is a chemical reaction. So what I'm going to do very quickly is I'll show you another video with a description of the process so that you can see why this is a chemical process.
White proteins, so they recombine with each other. They bounce all over the place. They bump into the water molecules. All this bouncing and banging breaks the weak bonds that keep the protein curled up tightly. The egg proteins uncurl and bump into all the other proteins that have uncurled. New chemical bonds form, connecting one protein to another.
Yes, I'm going to take it back a little bit.
Linkage. Today we're going to demonstrate linkage consists of a carboxylic group, eggs containing proteins which change OOH, combined with an amino group, symbolized by NH2.
Can you see it?
And now we're going to turn the pan on.
I can hear it, but I'm not seeing it.
Oh, I'll tell you
take the egg.
It's a shame, but I'm going to have to show you this.
Well, first.
I'm going to have to show you this. Maybe it's something we can send to you. I'll just explain exactly what happens so that we don't, yeah, because we've had a bit of a problem. Can you see my presentation at the moment? Can you see the PowerPoint slide?
Yeah.
You can see it. Okay. Okay. So basically, frying an egg is a chemical process. Chemicals, egg whites are made of curled up strands of something called amino acids, or they refer to as peptides. And what happens is when you heat up the egg, when you put your egg into the pot and you turn on the heat, these proteins are kept together by bonds, by chemical bonds. And what happens is when the eggs are fried, they absorb heat energy, and that breaks those bonds and allows, they break the bonds that allow the egg to keep its shape, and they start to uncurl, and they start to form other bonds. So just to show you what it looks like, if you were to look inside what the protein is made of, this is what you would see. So this is what a peptide looks like. What happens is these peptides are made up of two groups. They're made up of a carboxyl group, which is called a COOH. That's the chains that hold hydrocarbons together. And they're made up of an NH2 or amidogen group. And what happens is when you heat these up, they break up and they form bonds. And it's those bonds that you start to see when you fry the egg and you start to see it turning white. The problem is if you heat it up for too long, those bonds become a lot stronger, and it becomes, the egg starts to look rubbery, and that's why it happens. So that is an example of a chemical process because of a chemical reaction. So that the question we were asking is, what types of processes exist? You have physical processes and you have chemical processes, and you're engaged with these processes every day of your life. So here's a good example of someone who says they're hungry, they need to fry an egg, and somebody points out that that's a chemical reaction. They then decide that they'd like to mow the lawn outside, and that's a physical reaction. A chemical reaction typically leads to a change in the chemical composition of the material that is going through that process, whereas a physical exercise doesn't. So, for example, I could take a lemon and I could slice that lemon in two, and that's a physical process, because after I've done that, everything's still the same, it's only in two bits. Same with mowing a lawn. So you've got chemical processes and you've got physical processes, and chemical engineers are engaged with those. These chemical reactions happen every day and in every aspect of our lives. How many of you have cars, or maybe your family has a car?
I do.
Yeah?
We do.
Now, what happens is when you turn on the ignition, heat is applied to the fuel that you put in the car, so petrol, diesel, and fuel is generally made up of hydrocarbons. But fuels also have inside them, depending on the fuel, they also have inside them some nitrogen. The other place where you have nitrogen is in the air. So the process of burning something often involves having a fuel, like petrol, gasoline, or diesel. It involves having a bit of air, because the fuel must react with the air in order for combustion to happen. Also involves the presence of heat. Now, what happens is a lot of the air that we have is made up of a number of components, but the two greatest components or largest components in air are nitrogen and oxygen. Nitrogen is a molecule and oxygen is a molecule? How many people know what a molecule is? Have you ever heard of the term a molecule?
Is it a tiny little atom in every living thing or something?
Well, a molecule is made of, especially a molecule like this, made up of 2 atoms. And what happens is that when you heat up air up to a certain point, say maybe 1,100 degrees centigrade, when it's really hot, those molecules break up into atoms. So the nitrogen, which is usually in this form in normal conditions, and this oxygen often break up into their atoms, and they react with each other to form nitrogen oxide. That nitrogen oxide then gets oxidized, gets more oxygen, and that oxygen causes it to be formed to form nitrogen dioxide. And we usually refer to these 2 gases as NOx. So that's another example of a chemical reaction. And all of this happens every time you turn on your engine. Now, there's a way of getting rid of those nitrogen oxides, because those nitrogen oxides are bad for the environment. How many of you have ever heard of soda ash? Soda ash is a process, there's a thing called soda ash. How many of you have heard of it? Well, soda ash is a very important substance that is used in various industries. It's used to make soap, it's used to make glass, it's used for construction, it's used in many different fields, it's used to make various solvents. And that process, that chemical process, is created or produced by something called the Leblanc process. And what happens with the Leblanc process is that 2 reactants, 2 substances, get mixed together, they get heated up, and then they react, and the reaction eventually produces sodium carbonate. And I'll tell you a little bit more about that later. But you have a process of reacting common salt with sulfuric acid. That process produces sodium sulfate and hydrochloric acid. That hydrochloric acid is then reacted with carbon, and that process creates a combination of carbon dioxide and sodium sulfide. Sodium sulfide is then reacted with limestone, and that limestone creates soda ash and calcium sulfide. So this is what we refer to as a process. So basically what you do is you take 2 raw materials, you take it through a process, and that process creates something we call soda ash. Oh, sorry? Oh, I thought somebody said something. So soda ash is the valuable product that comes out of the process. Now, what we refer to, each step of this process is referred to as a unit operation. So unit operation involves a physical change or a chemical transformation. So the process that we've just been through now, is this a physical or a chemical process?
Did you have a question, Rowena?
Yeah. Please ask a question.
What is NOx?
What is NOx? So NOx is nitrogen oxides. Nitrogen oxides are these gases that get produced when fuels are burned. So when fuels are burned, especially a fuel like diesel, when it's burned, it has inside it some nitrogen. When you burn it, that nitrogen reacts with oxygen to form NO. And that NO is really bad for the environment. It's bad to breathe in, because when you breathe it in, it can cause problems with circulation. It's also bad for the environment because it's one of the gases that causes global warming. So global warming is the process by which gases evolve up and basically in the process deplete the ozone layer. We are protected by something called the ozone layer, and these gases, these nitrogen oxides, they evolve and they deplete that, which means that you and I get more heat radiation from the sun. So it's really bad, these nitrogen oxides, and that's what NOx is. Is that good?
Yes.
Yeah, thank you. That's great. That's great. Now we're gonna, so I'll go back to where we were. So yeah, so this is a process. So the question I'll ask you all is, this process that I've just described to you that is used to create soda ash, is that a chemical or a physical process?
A chemical.
A chemical process. Excellent, excellent. So this is a chemical process, and every stage of this process is referred to as a unit operation. A unit operation. And so it's these processes that chemical engineers work on. Chemical engineers are also interested in knowing about the property of fluids. So there are many other properties that we're interested in, but three of them that we're quite interested in are these three here. So density. Density is the amount of mass in a specified space. So if you can think of a container, say maybe a bottle, if you were able to put some stones into that bottle, say you were able to put just maybe half of it, and then you took another bottle and you fill that bottle all the way to the top, you would notice that one of these, the behavior of these two, or maybe even the sound that they make, would be different. And so the bottle that is full of stuff is your more dense bottle, because it has within this, it has exactly the same volume, but it has more stuff in it. Viscosity is another one that is interesting to us. It's basically the extent to which a liquid shows resistance to flow. So here we have an experiment where somebody had water, corn syrup, oil, and honey. And what they did was they took a marble, a little stone, and they dropped it in. Now what you find is the more viscous that fluid is, the slower that stone will settle. Another point that's very interesting to engineers, to chemical engineers, is the boiling point or the melting point. Substances exist in three key forms: solids, liquids, and gases. And the process by which a liquid boils off to become a vapor, for example, if you're boiling if you were boiling a kettle, the process at which the kettle starts to boil and you start to see vapor coming out of it, that's the boiling point. And if you had, say you bought some ice cream and you put that out in the kitchen, over time that ice cream will melt, right? And that process, the temperature at which that starts to melt, we often refer to as a melting point. So three things you need to remember: properties of fluids that we're interested in as chemical engineers. We're interested in the density. We want to know its viscosity, its resistance to flow, and we want to know the boiling point, the temperature at which it boils. Now, I'm going to ask you another question. Now, some of you said you had cooked, right? Now,
yeah.
Imagine that so how many people do you think could, if you were going to cook for a number of people, how many people do you think you could cook some food for with this pot? So say it was eggs. How many people could have eggs out of this pot?
I think around maybe 10.
Maybe around 10?
Maybe I'll say 10. I'll say 10.
Maybe 14.
10? 14? Oh, wow. Wow. That's those people maybe not very hungry.
8.
Any other suggestions? 14. You said 14. Okay, so
8.
what happens if you were asked to make this, if we all agree that you can only serve 14 people from this spot, what happens if you were then asked, if maybe your mum said, all of our neighbors are coming round and I would like you to make eggs for 50 people? What would you have to do?
I mean, I would take a
If
big
it was
pot,
10,
but
if the pot was able to if you're able to make 10 eggs in that pot, you'll have to get 5 more pots.
Fantastic.
You need to get 4 more pots, sorry. You need to get 4 more pots.
You're absolutely right. Yes, you would have to increase the number because you've got more people. The other thing you would need is you will probably need a few more tools, because you don't just put the pot in there. You have to use a spoon, don't you? So you probably need to use a few more items in terms of your equipment. So right there, this is what chemical engineers do. We take the reactions that chemists work on in the lab, or the processes that are worked on a smaller scale, and we scale them up so that they can help more, more products for more people. So the difference between a chemist and a chemical engineer, the difference between a chemist and a chemical engineer has to do with the scale. So whilst chemists work on new processes, they're very interested in new reactions, in ways of making reactions work better in the lab. Chemical engineers take that process and they scale it up. So if you don't remember anything else today, remember that chemical engineers scale things up. That's what we do. Now, how do we do this though? One of the things that we do is we do something called a mass and energy balance. So remember when I asked you—
Answer my question.
I'll tell you what, why don't we wait to the end and then I'll answer. Just write down your question and I'll answer. I want to get through loads of other stuff. So if you just write down your question, I'll answer at the end of it. Is that okay?
Okay.
Thank you, thank you. Now, one of the things that we do, remember when I asked you about cooking, and I asked you if you had to cook for more people, what would you do? And what you all did was you did a little calculation, didn't you? You said, well, if this can feed 14 people, then I'm going to need to provide 4 pots if I'm going to do this for 50 people. What you were doing there is you were thinking about the amount of raw materials that you need. You were thinking about the type of equipment that you'll need. So in this case, this was your 4 pots, or maybe even you could have thought of, instead of 4, you could have thought of a bigger pot. And you also think about the amount of heat that you would need. So that's your energy. So what chemical engineers do is we think about that whole process and we think, if you want to scale this up and we want to produce enough for a larger number of people, there are a number of things we have to think of. We think we probably need more heat. So maybe we need to use more than 1 hub on the cooker. We probably need to be careful because the more stuff you have to produce, the safer, the risk, the greater risk of something going wrong. And chemical engineers think about all of that. So we think about all the raw materials, we think about the energy that we will need, and what we want to do is produce the products. We want to find out what else is produced as a result, because there's such a thing as byproducts, and we want to know how much energy you're likely to lose. And what happens in some plants is that where you have a reaction that generates a lot of heat, what you do is you take that heat and you find a way to use it in the process so that you can be more efficient. So these are the things that chemical engineers have to think about. Now, I asked you all about soda ash before, and I said it's a very useful tool It's used to produce glass, paper, it's used for soap, it's used for various things. Now, I'm going to tell you a story about how soda ash is actually very important to how chemical engineering came to be. So many years ago, there was a something called there was a war or called the American Revolution, and when it happened, European countries who had prior to that imported their soda ash, which they needed for everything, they'd imported it from America. But when the American Revolution happened, the Americans put blockades so that they couldn't send trade to France, or they couldn't send it to other countries in Europe either. And so what happened is that everyone needed soda ash because they needed it for various things. The French had sodium chloride, which is basically like the salt that you use for cooking. That's sodium chloride. But what they didn't have was soda ash, and they didn't know how to make soda ash on a large scale. And so what they did, I've noticed somebody raised their hand. I'll answer your questions at the end of the session. So what happened is, at that time, the French Academy of Sciences, the Royal Academy of Sciences, actually put out a challenge to the whole country. They said, if anyone can produce this soda ash on a large scale, they were going to be given a certain amount of money. They were going to receive 2,400 livres. And the equivalent of that is, 1 livre is like a pound of silver. So if you have a pound of silver today, if you had 2,400 pounds of silver today, it will probably cost about £1 million to buy, because so there's a lot of money on offer for anyone who could produce this valuable product. So many people tried and failed, but after 15 years, a man called Nicolas Leblanc managed to do it. He did it in 1789. And what he did was he took that process of taking sodium chloride, he mixed it up with sulfuric acid, which is symbolized by H2SO4. Don't worry if you don't understand all of these at the moment. We will go into it in other sessions. But he took these two very valuable raw materials and he mixed them together, and they produced sodium sulfate and hydrochloric acid. He then combined the sodium sulfate that was produced, mixed it with carbon, and also mixed it with limestone, and limestone is calcium carbonate. And with that, he was able to produce soda ash, and then he was able to wash off the calcium sulfate so that he had that process. So he finally did what other people wanted to do and couldn't do. When he did that, he then decided to open a factory in a place called Saint-Denis, but he kept his formulas a secret, because obviously if you've got the formula, it means you were the only one entitled. But unfortunately, there was another revolt where the French were revolting against the king, or the royal family in France, and they did something called the French Revolution. And during the French Revolution, they not only they got the formulas that Mr. Leblanc had created, and they made it public to everyone. So unfortunately, Mr. Leblanc, he did all this work, but he never received the money that he was promised that for whoever created the process, because before they could do it, the French Revolution happened and the royal family was overthrown. Now, the process that was created was very bad for the environment, because something that can happen when processes happen, chemical processes, is they can have a real impact on the environment. So what you had was like really bad gases being polluting everywhere.
Greenhouse gases.
Well, some of them are greenhouse gases. Some of them are just bad to inhale. So they were really bad. And there was a man whose name was George Davis. George was an inspector. And when he was inspecting this, he was really worried about the extent to which these processes, which create a valuable product, but were really bad for the environment, he was worried about it. And so what he started to do was he started to put together a list of processes. He started to understand all of the manufacturing processes that were used to make various things, including soda ash. And he was starting to look for people who were not just chemists, but people with an understanding of physics, people with an understanding of how processes work, basically, so that you could make them more efficient and so you can make them more safe. And he started to bring together various people who had a similar concern. He was the first person to actually define the term chemical engineer. And so in 1922, after about 42 years of trying, he managed to get about 297 people to form the Institution of Chemical Engineers. In the process, he taught in Manchester Technical College, which today is referred to as the University of Manchester. And one of the key things he taught was that all processes can be broken down into relatively small numbers of operations. That was picked on by another chemist who worked for MIT in America. And Arthur D. Little was the first person to define the term unit operations. So that's how chemical engineering came about. I'm going to very quickly go through a number of processes that chemical engineers are involved in. Now, one of the very common processes is a process called simple distillation. Simple distillation is a process by which a chemist takes a mixture and uses the boiling point of the substances that make that mixture to separate them. This was the very first one done in the 3rd century by a guy called Zosimos, who was a Greek alchemist. He first came up with a way of distilling non-water liquids. There was distilled water before that. Now, the way in which chemical engineers use this process is something called, is something we use in a refinery. And a refinery is where we take crude oil, we heat it up, and then we break it into very useful parts. So you take the crude oil, and each of these, the crude oil is made up of hydrocarbon chains, and is made up of various substances that can be used for various things. And based on that process, we're able to produce different products which are very useful. So, for example, if you turn on your gas cooker at home to fry your eggs, you will probably be burning gas. The gas that comes through it comes from the top of this distillation column. It has to go through other processes, of course. When you when your car or your dad's car or mom's car runs out of fuel, they go to a petrol station, and that comes from these products that come out of a distillation column. I've actually been into one of these distillation columns. They can be so big enough to walk around. That's how big they are. The other process that we do is a process called cracking. Now, I mentioned before that hydrocarbons are made up of chains, carbon and hydrogen chains. Now, what happens with cracking is what happens when you break one of these chains. You break them either by putting them under extreme heat, or you put them under minor heat, but you add something called a catalyst. And with that, you're able to break it into even more useful parts. So the other thing that chemical engineers do is they break up on a big scale. So we're able to break things up, but we're able to do that on a big scale. So if you give that to a chemical engineer, this reaction, what they'll do is they produce something that looks like this. So they'll produce a plant that can take the same raw materials, the the same raw materials that come from your distillation column. They can subject that to a catalyst and put it in a reactor. And from that reactor, they're able to break it into smaller parts. So that's another example. Now, do you remember when I asked you at the start, which of these companies don't hire chemical engineers? Remember what somebody said? What was the company you said didn't hire chemical engineers?
I said Intel.
Right. So I'm sorry to disappoint you, but they do hire chemical engineers. In fact, they hire many chemical engineers. You know why? Because everything that they do has to go onto a board. It's like a wafer. So if you can see that everything they're doing, everything this guy's doing here is on a bed, which is a wafer. And that's used for everything that the electrical engineer then does. I could tell you a bit about semiconductors. You have substances that transmit electricity, and those are referred to as conductors. You have other substances that don't transmit electricity, and those are non-conductors. And then in the middle of that, you have other things that, if subjected to some heat, are able to conduct. And that's why they're called semiconductors. So chemical engineers make those too. Who knows what this is?
It's an exhaust pipe.
Exhaust of a car. That's right. Now, remember the reaction I showed you earlier with NOx, where NOx gets produced. Now, the other thing that gets produced is lots of carbon dioxide. And carbon dioxide and NOx are really bad for the environment. They're particularly very, very toxic gases that affect the ozone, deplete the ozone layer, and cause global warming, greenhouse effect. So what chemical engineers did, one chemical engineer designed something to deal with this. It's called a catalytic converter. So in almost every car that you drive today, you will have at the exhaust a catalytic converter. And what those do is they take the nitrogen oxides that are created, they combine it with an ammonia substance, and they take that and that reacts so that then reacts to basically convert it to nitrogen and water. It breaks off and it's able to deal with more than 90% of all the NOx that's created. So it's very important for the environment, and that's what chemical engineers do. Another very important process, and this will be the last of the processes. Another very important process is one called the Haber process, also known as the Haber-Bosch process. It's used for ammonia. How many of you know where ammonia is used? Can you give me an example of where ammonia, what things ammonia could be used for?
Gas.
Yeah, so. Any other suggestion? I'm going to give you a clue.
Compost for plants.
That's true. Well, I'm going to give you a clue. It's used for something that farmers use.
Fertilizer.
Yes, that's right, actually. But it's 90% of all the ammonia that's created is used for fertilizers. Who knows what a fertilizer is?
I know.
Go on, tell me.
It's used to make plants grow faster.
That's perfect. Yes. So if you've ever been on a farm, what you have is you dig up your soil, you put your seed in, and then you use some fertilizer to help the process. And chemical engineers are in charge of the processes that make that. So this is the Haber process on a large scale. Right. The next one I'm going to show you. So you may want to know at this stage, what are the other benefits of being a chemical engineer? There's so many benefits. You get to travel all around the world. You get to work in different places. I mean, I've worked in America, I've worked in France, and I've worked in different sites across the UK. But if you speak to some other people, they worked in so many other places. Chemical engineering is one of the most diverse in terms of the number of boys and girls, men and women who work in it. But here's another benefit for most graduate engineers. Now, we're not saying money should ever be your motivation for doing anything, but I thought you may be interested in knowing that of the graduates that start engineering degrees, chemical engineers start the highest. So because the work we do is involved in absolutely everything. Now, I'm going to also show you a picture of a few very well-known, famous chemical engineers. Actually, only one of these is still, well, only two of them are still working on it in a, still working as engineers. But it just shows you that chemical engineer gives you so many skills. It allows you to be able to do so many things. So the first one is a lady called Mae Jemison. She's actually been in movies. She studied chemical engineering at Stanford University. She also studied medicine, and she was the first Black woman to go into space. She's you can read up about her. She's a real inspiration. Dolph Lundgren is another person who studied chemical engineering, and he actually studied chemical engineering at the University of Sydney. He is now an actor and a filmmaker, and certainly when I was growing up, I watched a few movies with him. The next person is the president of the People's Republic of China, which is one of the most powerful countries in the world. Is led by a chemical engineer. His name is Xi Jinping, and he studied chemical engineering. The last person I'd like to show you is one of the richest, actually, people. He owns one of the largest businesses owned by a Black person in America. His name is K.C. Lowell, and he studied chemical engineering, and he started his career working for Shell. So remember when I told you about the evil genius that I was inspired by? I saw this and it made me laugh because it made me think about what inspired me to become a chemical engineer. So yeah, so that's everything I'm going to tell you about chemical engineering. So if you've got any questions, now's the time to let me know.
Why do people want to do this? Like pollute the air?
Exactly. It's very wrong to pollute the air, but this is why chemical engineers also make quite a lot of devices to stop that pollution. So very often these processes come about because we need things for everyday life. But over time, we have learned to make other processes to ensure that they are safe.
Does it mean does Shell employ chemical engineers?
Yes, they do. They do employ a lot of chemical engineers. In fact, all of those companies that I showed you earlier, L'Oreal, all the companies employ chemical engineers.
Does this mean it's chemical engineers that produce fertilizers?
Yes, chemical engineers produce the processes that give you fertilizer. Yes.
Thank you very, very much, Dr. Ollie. We really can we just unmute our mics and give Dr. Ollie a round of applause? That was a very, very, very great, insightful session. I feel like I'm a chemical engineer myself. So we'll just take one last question that someone put on the chat. He says, what are the disadvantages of being a chemical engineer? Dr. Ollie?
That's an interesting question. I suppose one of you may call it a disadvantage. Some people may think of it as a disadvantage. But one thing that engineers in general do, but I would say maybe it happens to chemical engineers, maybe a bit more, I'm not sure, is that you do end up sometimes having to travel a bit. You know, but depending on how you do it, it can actually be an advantage because you have people who get to see various experiences. So that's the only thing I can think of that some people may see as a disadvantage. But you know, if you can get to work in the Middle East, in America, you can work pretty much anywhere, and you get to have different experiences of different people. That is a good thing. So potentially that's one challenge, but it could be an advantage.
So if you love traveling, it's not a disadvantage.
That's right. That's right. You know, and some chemical engineers don't have to travel too much. So yeah.
Okay. So the last question we'll be taking is, please, what is sulfuric acid?
Oh wow, that's a really good one. Sulfuric acid, and maybe what we'll have to do is do a session on acids so that you know. The sulfuric acid is a substance. It's a substance that is very I don't want to use the word corrosive, but it potentially could be very dangerous, but if applied in the right way, can be employed to making different things. So whether it's car batteries and the way in which they work, or whether that's processes like creating some of the products that produce what we use every day, they're very good for that. So sulfuric acid is a corrosive substance, which if applied in the right way, can be used to make very useful products.
Okay, thank you so very much, Dr. Ali. We really, really appreciate that talk and that session. So I'm sure every one of us should know something about chemical engineering, what chemicals are, and a bit about the companies you can actually work for, okay? So next we will be doing a quiz. I'm sure most of you got it from the invite. We will be doing a next gen quiz, and the winners will be getting a prize. So that's going to be a surprise till the end. And afterwards, Dr. Renna would be giving out certificates, but I'll wait for her to do that afterwards. So if you've got a second device, please go to the link that I've posted in the chat. And if you don't have a second device, just put it on another tab in your browser. I've just put it again, and you should see a blue screen. So if you enter your name, so we know who actually won the quiz. So you should see a blue kind of screen. I'm just going to share my screen so you can all see. Is everybody there before I start?
Yeah, I'm here.
I don't see a link.
Yeah,
I'm not here yet.
Okay, so the link is in the chat. If you literally just copy that and paste it in your browser, or you can just type it in your browser.
Actually, I'm not here.
So it's paulev.com/MOPELOLAONAY784.
Do we have to sign in?
No, once you just put it on your browser, it should take you to this quiz. Just put your name. It's going to ask for your name, so we know who's playing the quiz. So the first question, remember you have to type this in really fast. So the trick is fastest fingers. So you have only 10 seconds to type the correct answer, okay? So these questions, there'll be 10 questions, and it's based on all the events and sessions we've had since March. So if you've been very, very regular, you would know some of the answers, or most of the answers to these questions. So the first question is, which of these is not a STEM career? Okay, so these are the options. So you need to click on the correct answer, and okay, so now let's see what the answer is. The correct answer is fine arts, and everyone got that. Well done. So we have AO as the winner and Esere as the second person. Well done. Next question. In the Achieving Your Dreams session, we carried out an analysis of our lives using what? So these are the options. Correct answer is SWOT analysis. So it tells you your strengths, weakness, and it was Dr. Urena who took that session. Well done, everyone. The leaderboard is still AO. Well done, Okane, for coming up. Next question. In the oil and gas rock session, we learned 5 steps to heaven. If you remember that, that was a very interesting session. What was the first step? It's not a trick question. What is the first step to heaven? Ooh, we had a mix of answers here. The correct answer is source. Well done to those who typed that in. Well done, Tishay. Tishay moved up to 3rd place. AO and Esere still take 1st and 2nd place. Next question. During the oil and gas exploration session, which of the following resources are found at the top within the rock formation? So we have oil, we have water, we have gas, and we have Coca-Cola. Well done. I was really hoping no one wrote Coca-Cola. So the correct answer is gas. Well done. Esere is now in 1st place. Well done. Next question. The top of the Louvre Museum is made from what class of material? This was in the session of exploring the materials that shape our world. So that's the Louvre in Paris. And what class of material is it made out of? So metal, polymer, composites, and ceramics.
How am I supposed to type it?
Sorry?
How am I supposed to get the answer?
You're supposed to be clicking on the answer. So not a lot of people got this. So it's actually made of glass, and glass is actually under the classification of ceramics. So if you're under the link, if you're in the link, Rowena, you should see the options to tap it, okay? Next question, leaderboard. Ayo has gone up. Oh, wow, he's on 2nd place now. Next question, from the materials that shape our world session, how many classes of materials are there? This should be an easy catch based on our previous question. The correct answer is 4. Well done to those who got that. Ayo is up on 1st place again. Next question, how many phases can we observe in one orbit of the moon around the Earth? This was Dr. Aras who took this. And that's it. How many phases can we observe? Is it 4? Is it 8? Is it 12? Or is it 16? Let's find out. Wow, a mix of answers. The correct answer is 8. Well done. I'm moving on to the winner. Let's see who's still on 1st place. Ayo, Esere, well done. Next question. The moon orbits Earth approximately once every day, week, month, or year?
Yeah.
Type that in. Don't need to tell me. Unfortunately, it's not year, it's once every month, and 44% of people got that. Well done. Femi is now in 1st place. Well done, Femi. AO is 2nd place, and Sophie is 3rd place. Next question. The product of the mass of an object and its velocity is called, this was in our physics session, Emmanuel took this session and was really, really interesting. So what's the correct answer? Well done. Most people got the answer. The correct answer is momentum. Well done, Femi, AO, and Ayo. Next question. And the very last question. From our computing session, one of the following is not a main primary component of the computer. What is the answer to this? Input unit, memory unit, central processing unit, and C programming unit.
My God.
The correct answer is C programming unit. Well done. And we have AO as the winner. I'm gonna have to, I don't know if Urena is here, if you can take a screenshot of the winners for today. So well done to AO.
That was so close. Good game.
It was good, wasn't it?
Yeah.
Well done to you as well. So AO was the winner. Titi came second. Esere came third. Femi came fourth. And Ayo came fifth. Sophie, Okin, and the rest of everyone, well done for even participating.
Mo, just hold on a bit. I need to, can you compress the screen because I can only see 7 names. Although we need only, yeah, I thought we could just get the 10 of them.
Oh no, it doesn't, I don't think it shows up to 10. I'll just show you, I think it shows 7.
Okay, that's fine. I have taken a screenshot of the 7. So that's what I have just now.
I have a screenshot of the 10. So
I
have a screenshot of the 10.
Oh, well done. So who was 8, 9, and 10?
8 was Luke R, 9 was Snivas Mahati, and 10 was Tishe.
Oh, well done. Well done to the very first 10 and to everyone really for participating because I'm sure you did a good job at least answering some questions.
Well done, guys.
Well done. Give yourselves a round of applause.
Well done, Roa.
So, Urena, I'll hand over to you. There'll be prizes. Urena, I'll hand over to you.
All right. Thank you very much, Mo, for that session. Thank you, Dr. Ollie, for your wonderful and insightful presentation on chemical engineering. I'm sure a lot of people are now aspiring to become chemical engineers. Well done.